Good morning, everyone. Okay, so a little busy because of the semester ending, and so I thought of now uploading this video today, and thought about what we can talk about. So, and given that we had some interviews recently going on, so I thought that it would be a good idea to review what is a MOSFET because we see that some of students, when we ask, they are quite confused in the understanding of the operation of the MOSFET. So it would be a good idea to look at what defines a MOSFET, how can you understand it. I will try to give best of my understanding, how we understand MOSFET, right? What are the different terminals, what happens in a MOSFET. So I think it starts with the application in understanding first that we have seen, which in the different videos, this has been one of the guiding, let's say, thing on any ICs, right? And that is why it is so important to know the operation and redesigning and what goes on. It tells you lot about semiconductor per se. So this MOSFET is having, we said, four terminals were there, which other terminal is not very clear from the symbol, but it is drawn also as a body, right? So these are the things which you may not know, but let's say if you're using in circuit, then you know that there is a, the basic idea is that if I want to, there is something flowing like a river flowing here, right, which is the current, and you want to control using this thing, which is your control terminal. That is the basic idea of a MOSFET, which is what we saw also with the water analogy, where you have a tap, right? And we saw that in a tap, if you are having a flow of water, right, then this flow is controlled by this control terminal, right? And that is what your gate is in this, and this is the whatever drain to source, whatever is flowing, right? Or source to drain. So that is the kind of analogy for seeing the current or the flow. Now the question is that how does one realize it, right? What is the physical structure to do that? So you see that there is a control terminal and there are two terminals between which is, this is flowing, right? There is a river flowing between these two terminals. So the three terminals are very, very evident that these are three terminals. So first, let's see where this current flowing, right? What is constituting the current, right? So that comes a question: what is constituting a current, right? And where does it flow, right? So that becomes a question. So then we see that okay, that basically this is a very it could flow, let's say for example, of any material, right? Where we apply certain potential, we understand that we apply certain potential to this material, then it could be it could be a metal, it could be a conductor, right? Or it could be a semiconductor, whatever different materials you have, or even an insulator, right? You are going to apply you are going to see some current flowing through this material, right? So that is what one analogy of the flow of the current. And this current, we know that this is being carried, or what constitutes to the current is the electron, right? That is what we have been seeing, and that is what the whole electronics is based on, right? Now, where is this electron? Obviously, it's inside the material. So then if we little bit zoom into the material may look like this very simple model, that there are different atoms which are connected to each other, right? And these uh, connection, when there is a thermal energy or whatever there is there in the system, there are some bonds which are broken, which gives you this electrons, right, which are there in this system. So these electrons are the ones which are based when you apply a potential difference. You see that what is going to happen when you apply potential. You are going to see an electric field due to this, right, in this direction. So if you see an electric field in this direction, then you see that okay, this guy is going to feel a force because electrostatic force, which is your QE, and it's going to feel a drift, right, kind of. And this is why we see that when we are applying an electric field into this, there is a current which you see due to drift, right? Right, of electrons. So that is what is constituting, you see, the kind of current, or where does it flow? We see from one terminal to another terminal, right? That is the basic idea. Now the question is, okay, this is good, now, but how do I bring in the control terminal, right? What is the control terminal doing? So one thing which you see clearly in the tap, that the control terminal, what was it doing? It was kind of putting a barrier, something, right? So the barrier goes in from the control terminal, and then you see that there is nothing going, right? So then the role of the control is terminal to put the barrier and remove the barrier, right? Barrier and remove the barrier. So that is how you can control the flow of current, or because this electric field is what we are applying. So you can think of this as an analogy of the drain and source, right? Which is what we are applying, right? Or the other way around, right? Where you see that the electron, if it is basically from here, you will see the drift. It's happening this way, right? Of the electrons. And the current which is flowing obviously is the other direction of the electron, right? That is the convention of the current. So then we see that, okay, whenever I apply this VDS, I'm going to see a current flowing. But if VDS is 0, right, then there should not be any current flowing. This should be 0, because there is not enough, or there is no net force on the electron to drift, right? That is the reason. No net force on electron to drift. That is the. So now you see, okay, this is the basic understanding of the flow of the current, which is any resistor or anything which you have seen, right? How do I put a barrier inside this device is the next thing which one would wonder, right? And that is where we figure out, okay, if this was a metal, let's say if you were doing this as a metal, and you put in a barrier there, right, which you can remove. Now it's not a physical barrier like a tap, right? You have to remove it using electrically, and electrically we use voltages and current, right? That is what we use is current to control something, right? This is what we can use to control. Now in metal, if you see, you put a voltage, for example, how can you control? That is the question you can ask, unless you change some physical structure of the metal, right? So that becomes difficult. And that's where we see a very interesting uh, device, or very interesting structure like this, which metal oxide and semiconductor, right? And this whole series is about semiconductor, where you see that by applying this voltage here, which is our control terminal, which in effect generates an electric field, right? This is positive, this is negative. This electric field can now control the barrier. How does it control the barrier? You can ask me this question, and that you see when you put in a positive. So let's see, how does it, what is the state of the semiconductor? How does it change, right, when you put in a voltage? So let's take, initially you could take, let's say for example, a p-type semiconductor. So when there's a p-type, that means, in a p-type semiconductor, which we have talked about in detail in generation recombination or doping videos, that the lot of holes are there, right? Which that this is the definition of p-type semiconductor. And you see now the electric field, if it is in this direction, the hole is going to feel a drift into this direction, right? Because there's a drift, and then it is going away from the surface, right? And then if you keep applying this, then you see at some point your electrons which were there also, or which are generated. So this is very important, that this could be generated carriers, generated inside the semiconductor, right? What they would do, they will go to your surface, because they are going to feel the drift in the opposite direction, right? So in the end, you may see, when you apply a positive voltage, what you are going to see a lot of electrons at some point here. Right? We are not going to talk about the threshold voltage and so and this, because the idea is just to first figure out how to make this and where, because I am seeing that people, when they remember from the memory, they are forgetting what is gate terminal, what is drain terminal, right? This is my attempt to tell you how to even construct this device, right? How to think about this device. So you see the electrons come in now here. So now you see that this channel or this thing, you have kind of changed the property of this part, right? And how did you change the property? By applying a voltage or the field through this stack, right? That changed the property. So how did you change the property? Because earlier there were holes here, right? There were holes here. And now it has changed to an electron layer just by applying a voltage. Wow, something interesting happened, right? Of the, let's say, this channel layer, right? So now one can say, okay, if that is the case that you are able to change, why not now I can, because this, what does this do? This brings in just the change the property of the semiconductor. Is there any current flowing yet? No, because the reason is that if you have, even if the electrons are there at this side and they feel the drift to go to that side, this oxide creates a barrier for these electrons, right? It's a dielectric. So there is a huge barrier which they see. So these electrons are not going to flow to the top side through the dielectric. And that's why you see your gate current, whatever you measure, is going to be negligible, right? Very, very less current. Because if your dielectric is holding or your oxide is holding that its front, that I cannot let the electron go, then this current would be very less. So then the question comes, okay, that now if you change the property of this layer, right, you have changed the, by applying a voltage, how do I make the current flow? And which we have seen earlier, obviously, that you just apply that you need two other terminals to make a drain and source, because this was just grounded. So this is the body which we talked about. This is the gate. Now in this two terminal device, I need to add, right? This is my metal. This is my oxide. This is my semiconductor. What I need to add is another piece of semiconductor, and where now I'm going to apply these biases, which I just saw, source and drain. So when I apply this bias, then only the current will flow. If this bias is not applied, even if you have changed the property of that region, right, without VDS, no current flows. No current means the drain to source, because the drain and source terminals are not there, right? And the gate terminal, we already saw that it's blocked by the dielectric. So then it becomes very important to see that, okay, how you can tune, because you see the p-type semiconductor, right? So if this was p-type and you, let's say, dope this part where this properties, let's say p-type, these two, so then you are seeing that even if you don't apply any gate voltage, right, zero gate voltage, because it's a p-type, there is no barrier you are going to feel. So the whole, right, it's going to have a free ride. If you apply an electric field in whatever direction, let's say if you apply like this, go whole is going to feel a free ride into. So in this case, we have to apply electric field like this if we want hole to go from source to drain, right? So that means that we see in this case that hole can go through this, right? And now if we make it positive n, then you see it would shut off, right? That is what is happening. So you see that if we make it positive, then this property will change, right? This there would be, because of this, there would be electrons here, and then there would be a barrier for the holes to go, right? So this is how you can think of the operation, which we call as the p channel effect. Why p channel? Because you see the barrier, the when it is p type, the interface is p type, right? Then there is no barrier. So that is the p channel effect for you, right? There's another counterpart of this we can draw is obviously your where you can say, okay, this is my metal, this is my oxide, this is my semiconductor. It is P type. Okay, no problem. But I know that when I apply positive voltage, this becomes a channel, right? So then you say, okay, I'm going to now put whatever pockets you put. You're going to put N plus pockets here, right? So what it does is now, because this is N type, your electrons which are here, right, are not going to feel any barrier. So if your electric field is applied this side, your electron will move this side. And why is it not feeling barrier? Because it sees a bridge. This is a bridge, right, which is what we know as the channel, right? So I used to understand this as when I was a student as a bridge, which is like if I have to go from one place to another place, because these has a lot of electron, these have a lot of electron, and if there is no bridge, then I have to jump. And if the distance is very large, then obviously I would not be able to reach to the other side. Then I saw, okay, if there was a bridge, then it would become easy for me. So bridge is basically removing the barrier, right? That is what you have done. So then that means initially with at zero, the state was providing a barrier, right? This was like this. So this was a P type and this was N plus. So there was a barrier because electron felt, oh, there's a P type there, right? So at Vg equal to 0, this felt a barrier, but at Vg positive, this does not have a barrier. But when does the current flow? It does not flow with Vg being high. Vg being positive or Vg is only controls the channel formation, let's call it, right? Channel formation, because this bridge is a bridge formation. What flows the current in this is this source and drain. So without source drain, without, so we understand that without or with or VDS is responsible for the current flow, right? That is what we see. Controls okay, or control is not the right word, because control we already see Vg is the one which controls the charge, so makes the current flow. Okay. So that is very important that you understand these terminals when you are studying about MOSFET, so that you don't get confused again and again. And one can see that based on now when you are looking at current, you have two different voltages, which is, so this is your N channel MOSFET. So you can see that based on the two voltages which you have now, you have a possibility, because the Vg is controlled. So that means you can say if I have three terminal like this, one can be my reference terminal, right? And based on this reference terminal, then I can define there is a voltage VGS and there is a voltage VDS, right? And then the output variable which I'm having is IDS. So obviously then you can have two characteristics. One is the ID VDS, YD VGS and IDS VDS, right? This is what is the control characteristics or your input characteristics, right? And this is your output characteristics. Okay. And then one can talk about what is there in this characteristic, how does that relate, all of that. But first thing I think is to not get confused in the terminals, that and understanding the role of each bias, what does it do. So that is why I thought of recording this, so that you can look at it again, right? If you want to, that how does it come to be? How do we make this? Where does it start from? So thank you, and keep growing, keep learning, all of you. Bye bye.